This video begins the lectures covering the forces of friction. For those of you enrolled in Physics AB, this begins the second half of Chapter 4. For those of you enrolled in Honors Physics AB and AP Physics C, this then begins Chapter 5. We recognize that there are two distinct forces of friction. There is, first of all, what is called the force of kinetic friction. The force of kinetic friction occurs between two surfaces that are moving relative to each other. And then secondly, distinct from kinetic friction, is what is called static friction. Static friction occurs between two surfaces that are not moving relative to each other. Take a moment to pause here such that you can write down this information. Okay, now let me go ahead and demonstrate the two forces to you and also show why they are in fact distinct from one another. I'm going to use my inclined plane here and my eraser to illustrate. Now, of course, we will be taking into account the friction that occurs between the eraser and the inclined plane. Okay, let me go ahead and set up the inclined plane here at a rather shallow angle of inclination. And I'm going to take the eraser, I'm going to send it down the slope such that when I release it, we'll have some speed in this direction. Even though it's moving downhill, however, because there's friction between the eraser and the inclined plane, and I only have the inclined plane here tilted at a relatively shallow angle, you're actually going to see the eraser slow down. That is like so. Okay, so while it's slowing down, its acceleration vector is up the slope like this. And then parallel to the incline, we actually have two forces acting. There's first of all the component of gravity pointing downhill, mg sine theta, and then opposing that is the force of kinetic friction acting upon the eraser up the hill. Those two forces then add together to give us mass times acceleration, where the acceleration is in this direction. However, now take a look at the situation. Notice that the eraser is now stationary relative to the incline, so then therefore essentially holding it in place is a force of static friction. In this case, the acceleration is 0. Therefore, the mg sine theta down the slope is being exactly canceled out by the force of static friction acting upon the eraser up the slope. Numerically, in the two situations, kinetic friction like so, and now static friction, the two forces have different values. Therefore, they are distinct from one another. Okay, now let me go through the basics as to where friction ultimately arises from. And as I do, you'll now understand exactly why there is no such thing as a frictionless surface. Okay, by the way, speaking of friction, like so, there's kinetic friction. Only in a physics class can the act of erasing the whiteboard actually be considered a demonstration. Here's a demonstration, by the way, of static friction. Like so. Force of static friction is holding the board in place. At any rate, however, let's see exactly where the forces of friction arise from. Okay, so from where do the forces of friction arise? Okay, well, let's say that you have two very finely polished surfaces. They feel very smooth to the touch. Let's say that you could somehow examine those surfaces by using a very powerful microscope. What you will find at the molecular level is that those surfaces are actually anything but smooth. They basically more or less look something like this. All right, so let's say that we have two finely polished surfaces, and we now look at those surfaces with a powerful microscope, like an electron microscope or something like that. Okay, well, let me go ahead and draw one of the surfaces kind of like that. And then using a separate color, here's another surface like that. And then let's just say that the two surfaces are moving relative to each other like so, for simplicity. You're going to get all sorts of mechanical forces that occur between all of the bumps and jags and so on and so forth of this blue surface here as it brushes up against right here the red surface like so. So then therefore at the microscopic level you have this mechanical interaction that occurs between the two surfaces. Mechanical forces arise, and that then of course is what we see as the force, say, of kinetic friction in this situation. So mechanical forces occur. Okay, that's pretty simple and also pretty obvious. However, this, as it is right now, doesn't fundamentally explain ultimately where friction comes from. In order to describe that, we actually have to go all the way down to the atomic level. So imagine that you have two perfectly smooth surfaces. Those surfaces literally consist of a single sheet of atoms. It is, by the way, possible to machine such surfaces today. Even so, you're ultimately going to have the forces of friction occur for the following reason. Okay, so now let's say that we have two perfectly polished surfaces, where each surface is a single sheet of atoms. So imagine that one of those surfaces looks like so. These circles that I'm drawing here, think of them as a representation of the electron clouds associated with the atoms of that, let's say, blue surface. Okay, and then we've got some red atoms here like so for this red surface. Once again, think of the circles here as representing the electron clouds associated with those atoms. And then just for simplicity, let's say that these two surfaces are moving relative to each other. At a fundamental level, the nature of matter is electromagnetism. In other words, there's an electromagnetic interaction that occurs between the electron clouds of the blue atoms here and the electron clouds of the red atoms. That electromagnetic interaction is fundamental to nature. The force of electromagnetism is one of nature's fundamental forces. Ultimately, this is where friction comes from, this interaction that occurs between these sheets of atoms. And this ultimately explains why there is no such thing as a frictionless surface. So we have, in a fundamental way, a fundamental interaction due to the force of electromagnetism. Fundamentally, this is where friction comes from. Okay, now we actually understand perfectly well today, that is, it's pretty complicated physics, but we do understand perfectly well today the electromagnetic interaction of matter with other matter. All of that fundamental physics is very well understood today. So we could describe exactly, for example, what happens, say, when this atom here interacts with this atom. However, computationally, it's actually impossible to go from a description of what is happening here at the atomic level and then ultimately derive exactly what is going to happen, for example, when this eraser slides across the incline like so. The reason why this is an impossible problem to solve is that there are just simply too many variables. There are trillions upon trillions of atoms that make up the surface of the eraser, trillions upon trillions of atoms that make up the surface here of the inclined plane, and then therefore using this fundamental physics to derive exactly what is going to happen to the eraser as it slides across the board like so is computationally an impossible problem to solve. It's similar to like trying to predict the weather accurately more than a couple of weeks in advance. We understand perfectly well what happens, for example, as sunlight enters the Earth's atmosphere. We understand perfectly well what happens with, say, air currents and wind patterns and so on as the Earth rotates. We understand perfectly well what happens when sunlight is absorbed by the ocean, etc., etc. We understand all of that physics extremely well. Therefore, why can't we use that physics to accurately predict the weather more than a couple of weeks in advance? Once again, there are just simply too many variables. It's a similar type of problem to what I'm describing here. However, it turns out that at the macroscopic level, in other words, at the level of ordinary everyday objects, both kinetic friction and static friction obey a few simple empirical properties, and they're actually mathematically really easy to describe. Recall in scientific lingo that the word empirical means based on data, based on observations. So based upon quantitative observations of the motions of objects around us, like say for example, as the eraser slides down the inclined plane, it turns out that mathematically describing the forces of friction acting upon the eraser are easy to do. So I'm going to go ahead and conclude this portion of the lecture here, and then in the next series we'll go through forces of kinetic friction and also forces of static friction.